Greetings, fellow learners. Welcome to the special video on the evolution of neural networks. In this video, we are going to see from neurons how they evolved to networks, both structurally and also their learning procedures, how and why they evolved over time. And so I'm hoping we'll also peel the curtain behind why neural networks exist the way they do today. So stay tuned, it's going to be fun. For this first pass, let's try to get an understanding of why the artificial neuron was created. So to do this, we go back to 1928 with the mathematician David Hilbert, who posited a question: does there exist a mechanical process to prove any mathematical statement as true or false? Now, Alan Turing took a stab at answering this question, and in order to do so, he first needed to define what is a mechanical process. And he defined this to be a sequence of steps that requires calculations or computations. And once he had this definition, he devised a Turing machine. A Turing machine is an abstract machine that, one, it provided a framework for creating a mechanical process for a given complex problem. And two, it proved the problem as either true or false if the problem was decidable or computable. And so, to answer this question that David Hilbert posited of whether there exists a mechanical process to prove any mathematical statement as true or false, Alan Turing replied with the negative, and specifically highlighting that there exists some mathematical statements or even problems in general that cannot simply be boiled down to an answer of either true or false, and these were considered undecidable. And one example of such a problem is like the halting problem. Something that's important to note here is this first point about the Turing machine. That is, the Turing machine provided a framework for creating a mechanical process for a given complex problem. Now, restated, or explicitly stated, the Turing machine provided a framework for solving complex problems by breaking them down into manageable steps that require computation. And now this was kind of the idea that was used by two people who were Walter Pitts and Warren McCulloch, one a logician and another a neurologist. Now, these two were interested in cognition and intelligence, and so they wanted to understand better biological neurons. Now, they made use of this statement, that is, that the Turing machine provided a framework for solving complex problems by breaking them down into manageable steps that require computation. And what they did was they took a complex biological neuron process and broke it down into manageable computation steps. And in doing this, they created a computation model of a biological neuron known as the artificial neuron. Quiz time! It's that time of video. Have you been paying attention? Let's quiz you to find out. Why was the artificial neuron created? A, to better understand the biological neuron. B, to better understand intelligence. C, to solve complex problems. Or D, to compete with the Turing machine. Note that multiple answers here may be correct, and I'll give you a few seconds to answer this question. The correct options are A and B, but can you tell me why? Give your reasoning down in the comments below and let's have a discussion. And if you like what you're seeing here, please do consider giving this video a thumbs up because it'll really help me a lot. Now, that's going to do it for quiz time and pass one of this video, but keep paying attention because I will be back to quiz you. In this pass, let's actually go through the workings of a biological neuron. Note that in the 1940s, not all of this information was known, but at least the high-level details of a rough outline were kind of known. So with that in mind, let's get to it. So we have this nerve cell over here, and it consists of dendrites, a cell body, which is the soma. Then it has an axon, as well as axon terminals. The myelin over here is a fatty substance that wraps around the axon. Now, how does this biological nerve cell actually carry a signal? So, first of all, the signal will be propagated from other cells that preceded it. So we have the axon terminals from other cells. There'll be hundreds and thousands of these. Now, at each of these intersection points of the axon terminals of the previous cell, as well as the dendrites of this current cell, they are known as a synapse. And if we kind of magnify this synapse, we can kind of see here is the axon terminal of the previous cell. Here is the current cell's dendrite. And we have these dots over here that represent neurotransmitters. These are like chemical messengers to transmit a chemical signal from one cell to the next. And then the dendrites over here consist of these tiny receptors, where when they come in contact with a neurotransmitter, there are ion channels within this nerve cell that will open up that allow the flow of positive or negative charges. So these could be like positive sodium ions or negative chloride ions. They can flow in and out of this cell over here. Now, if there is a net influx of the positive ions, then this means that there has been an excitatory postsynaptic potential. Postsynaptic here is on the side of the synapse of the output end, which is like the dendrite over here. Now, if there was a net influx of negative ions, however, in this dendrite, we would see that there is an inhibitory postsynaptic potential. Now, it is in this way that we have a chemical signal over here in the synapse converted into charged electrical signal. So let's actually get a better understanding now of the overall flow of how a signal is transmitted from one end of the neuron to the other. So first of all, we have this entire nerve cell that is sitting at a resting membrane potential of negative 70 millivolts. And when we say a resting membrane potential, it is the charge of the nerve cell minus the charge of the area surrounding the nerve cell. And that typically sits at negative 70 millivolts when there is no signal that's propagating through this nerve cell. Now, as a first step when transmitting a signal, we would have neurotransmitters that release from axon terminals of the previous neuron into the receptors of the dendrites over here. So that's our chemical signal. Next, this causes ion charges of whether it's sodium, calcium chloride to flow in and out of the neuron, changing its charge. And this could either be excitatory or inhibitory. Now, if the membrane's potential now crosses a certain threshold, that is over all of these individual synapse regions, if it crosses a certain threshold, which is typically negative 55 millivolts, this triggers an action potential, and an electrical signal will then be propagated through the axon. And when this happens, we say that this neuron has fired. Now, we have this myelin over here, which is a fatty substance that enables faster transmission of charge through the axon. And when the electrical signal reaches the axon terminals, this triggers the release of neurotransmitters, and the process then starts again for the next cells. So this is kind of the overall picture of how signals are propagated through a biological neuron. Quiz time! It's that time of video again. Have you been paying attention? Let's quiz you to find out. When does a neuron fire? A. After the difference in charge inside and outside the neuron exceeds some threshold. B. After the difference in charge inside and outside the neuron goes below some threshold. C. After the neurotransmitters enter the dendrites. Or D. After the axon carries an electrical signal. Note that multiple options here may be correct, and I'll give you a few seconds to answer this question. The correct option is A, but can you tell me why? Please give your reasoning down in the comments below and let's have a discussion. And that's going to do it for quiz 2 and pass 2 of this explanation, but keep paying attention because I will be back to quiz you. Now in this pass, let's actually talk about this artificial neuron. So we have McCulloch and Pitts who wanted to understand intelligence, and specifically so, they wanted to understand the intelligence that derives from a single biological neuron. Now, they kind of knew some of the complex signal processing of the neuron that we discussed in pass 2, but they had to make a lot of assumptions too. And what they were thinking here was that, well, let's break down this complex biological process into manageable computation steps, kind of how like Turing did back in the 1930s. And so they created what we call today the McCulloch-Pitts artificial neuron. So this artificial neuron is a computation model of a biological neuron designed to understand intelligence capabilities of said biological neuron. Now, model is a simplified representation of, well, a biological neuron, and computation model means that this simplified representation can be broken down to a set of steps that require just calculations in general. And we're going to take a look at those calculations and compare it to the actual biological process now moving forward. So here's the structure of the McCulloch-Pitts artificial neuron. We have a neuron that consists of inputs, weights, and outputs. So first of all, in the biological neuron, we mentioned that there is neurotransmitters released from axon terminals of the previous neuron into the receptors of the dendrites. Now, in the artificial neuron, this is represented through the inputs, where the inputs indicate signals from other neurons. So if, from the axon terminals, there was no signal from other neurons, we would say I over here, this I would be 0. But if there was signal, that is, there were like neurotransmitter signals that were received by the dendrites, then we would say that I is equal to 1, which indicates that like a signal has occurred or is input from the neurotransmitters from the previous cells. So these are essentially inputs from the previous neurons. Now, in the biological neuron case, this causes the ionic charge to flow in and out of the neuron, changing its charge, and this could be either excitatory or inhibitory. Now, this excitation and inhibition is kind of given by the weights. They represent the charge of the dendrite. So the weight W is equal to 1 exists if there is a net positive charge or there is an excitatory response. And W is equal to -1 if there is a net negative charge or an inhibitory response. So we have W1 and W2 can take different values of 1 or -1. Now, back to the biological neuron. Now, if the membrane potential crosses a certain threshold, this triggers an action potential, and then we say that the neuron has fired. Now, in our artificial neuron, the way that we represent this is that we have a membrane potential. This will be the sum of all of these weight products and input products over here. And then we'll have a threshold potential that is going to be T, some threshold. And we'll have an output, which will be a binary output that represents 1 if the neuron fires or 0 if the neuron does not fire. And we will determine this if the membrane potential is greater than a threshold, the neuron fires. If the membrane potential is less than a threshold, it does not fire. And so we have boiled down a complex biological process into a sequence of calculations in a much simplified version of the biological neuron, and hence this is a computation model. Computation because of calculations, model because it's a simplified representation of the biological system. And so we have the McCulloch-Pitts artificial neuron. Now, one of the major pros here is that, well, this artificial neuron can perform propositional logic. And for example, what I mean by that is we can actually create logic gates. So we can simulate an AND gate from just a single neuron. So if we set the threshold as 2 and the weights to be 1 and 1, then 2 inputs that are 0, this will be, we're going to have a sum of products, which is going to be 0. It's not greater than 2, and hence the output is 0. So 0 and 0 is 0. Similarly, 0 and 1 is 0. And then we have 1 and 0, and that's going to be 0. And 1 and 1 is 1. So it functions as a proper AND gate. Similarly, you can see that it functions as an OR gate too. In this case, we need to set the threshold to be 1. The weights remain the same as 1 and 1. So 0 or 0 becomes 0. 0 or 1 becomes 1. 1 or 0 becomes 1. And then 1 or 1 becomes 1 too. In a similar case, it also functions as a proper NOT gate. So let's say the threshold here now is 0, and the weight, there's only one weight, so it's -1 because there's only one input. We have 0 times -1, which is going to be 0, and it's greater than or equal to the threshold, hence it's 1. So input 0, output 1. Similarly, if the input is 1, the output will be 0. So interestingly enough, though, this is just a single neuron performing these operations. And we can even connect these single neurons to create a network of neurons, a neural network, in order to perform more complex logical operations, for example, like XOR. So each of these little things, whether it's AND or not, these are individual McCulloch-Pitts artificial neurons. Now, a con here, a major con, is that there is no effective learning procedure. So every single time that we have a neuron and we want to perform a certain process, we need to explicitly set the weights and the thresholds by hand. However, this is not how the brain works. The humans learn. And so if I were to summarize the entire thought process, the works and the conclusions of McCulloch and Pitts, it would go something like this. To understand human intelligence, we created a computation model of a biological neuron called the artificial neuron. A network of such neurons is capable of propositional logic. Now, while it is not clear that the complex biological neural networks perform logic in this way, it is a starting point. So, I hope all of this now makes sense. Quiz time. Ooh, this is going to be a fun one. Unlike a biological neuron, the McCulloch-Pitts neuron, A, can only accept binary inputs. B, has a concept of memory. C, cannot learn from data. Or D, is a computation model. Note that multiple options here may be correct, and I'll give you a few seconds to answer this question. The correct answers are A, C, and D. But can you tell me why? Give your reasoning down in the comments below and let's have a discussion. And if you do think I deserve it at this point, please do consider giving this video a like because it will help me out a lot. And that's going to do it for quiz time and pass 3 of this explanation. But before we go, let's generate a summary. So in this video, we started looking at the McCulloch-Pitts artificial neuron. And the artificial neuron is a computation model of a biological neuron designed to understand intelligence capability of said biological neuron. It's a model because it's a simplified representation, a computation model because we can break this down into a set of steps that are computable or calculatable. And so we established the relationship between a biological process of signal transmission and boiled it down to a set of mechanical steps right here for the artificial neuron. We then started talking about the pros of how it can function as logic gates and perform propositional logic, but also highlighted the con that there is no learning procedure and that this is not exactly how the brain works. And then we finished with our well-rounding statement that is, to understand human intelligence, the computation model, which is this artificial neuron, was created, and a network of neurons could perform propositional logic, but this is not necessarily indicative of this exactly is the way that the biological neural network actually performs logic. But it's a starting point. So for this neuron, how does this exactly learn? Well, We have Donald Hebb, who is a psychologist who came onto the scene in the 1940s, who stated that neurons that fire together wire together. And this is kind of the summarization of Hebbian learning that he proposed. Now, I'm going to describe a very simplified representation of what this looks like in action. So let's say that we have a very simple network of 3 neurons, and I'm going to illustrate something known as eye blink conditioning to illustrate a simplified form of learning. So one of the neurons here is a somatosensory neuron for detecting stimulus. Let's say in this case, it's going to be in the eyes. We have an auditory neuron to detect any kind of auditory stimulus. And then we have a neuron that's responsible for the motor skill of blinking, the action of blinking. Now, this by nature, the synapse over here is going to be strong, which means that whenever, let's say something enters your eye or your eye is stimulated, you are likely to blink. And so, hence, this synapse is strong. And similarly here, from an auditory neuron, if you hear something, you're not really likely to blink, and hence this connection or synapse is going to be weak. So what that means is, let's say there's a puff of air that enters your eyes, it's going to trigger your somatosensory neuron here and cause it to fire. Now, this is then due to the strong synapse. It's going to have a large number of neurotransmitters that are emitted over here. That's going to create an action potential and cause this neuron over here to fire. And hence, whenever there's a puff of air that enters your eye, you are likely to blink. Now, let's say now in a second case, you just hear the sound of some buzzing in your ear. Now, this is going to go to your auditory neuron. Now, your auditory neuron is going to fire. But because of the weak synaptic connection between the auditory neuron and the neuron responsible for blinking, there's not going to be a high enough potential generated in order to make this neuron for blinking fire. And so when you hear the sound of a buzz, you don't really blink, which makes sense. Now let's hear the third case, where you get a puff of air and a sound of a buzz at the same time. This causes their respective neurons to both fire. And now, because we have this visual neuron that's firing, it's going to cause the neuron responsible for blinking to also fire. And what you now notice here is because, by product of this, you will have an auditory neuron fire and this neuron for blink fire at the same time. They are firing together, and this causes a strengthening of the synaptic connection between them. And so, if we repeat this process of getting a puff of air and a buzzing sound, causing the neurons to fire, it's going to continue to strengthen the synaptic connection. And this, after repetition, will come to a point where when you just hear the sound of a buzz, it's going to cause the auditory neuron to fire. And because now this is a much stronger synapse, there's going to be more neurotransmitters that are able to go from the axon terminals of this first neuron to the dendrites of the second neuron. This can cause a rise in potential overall of this entire dendrite, and this can cause the action potential to be generated, and hence the neuron responsible for blink is going to fire too. Now, this action of hearing a buzz and then blinking was not something that was there before. And hence, we say that some learning has happened at this very fundamental 3-neuron level. And so this is kind of the big idea that's being proposed with Hebbian learning. Neurons that fire together, wire together. So with McCulloch and Pitts in 1943, they created a simplified representation of the complex neurological process through calculations or computations with the artificial neuron. Now, Donald Hebb in 1949 proposed Hebbian learning, which demonstrates the link between neurophysiology, that is like synapses and neurons, with psychology, which is learning. And so summarizes neurons that fire together, wire together. Now, taking advantage of these concepts and also some other research at the time, you have Frank Rosenblatt in 1958 create the perceptron. This is a computation model of a biological neural network with the ability to learn from feedback. So just like the artificial neuron, it is a computation model of a complex process. In this case, it's like a neurological process. But like Hebbian learning, it has some ability to now learn. And we're going to take a look at some higher level details about this perceptron in the next pass. Quiz time. Have you been paying attention? Let's quiz you to find out. According to Hebbian learning, learning is A, information stored as a coded representation in the brain. B, it's a property of the nervous system with information stored in the axon. C, it is a property of the nervous system with information stored in the synapse. Or D, none of the above. Note that multiple options here may be correct, and I'll give you a few seconds to answer this question. The correct answers are C. Now, can you tell me why? Give your reasoning in the comments below, and let's have a discussion. And if you think I do deserve it, please do consider giving this video a like, because it will help me out a lot. Now that's going to do it for quiz 1 and pass 1 of this explanation, but keep paying attention because I will be back to quiz you. Alright, so in this pass, let's take a look at some high-level details about the perceptron. This is a screenshot directly from Frank Rosenblatt's perceptron paper back in the 1950s, where we have this simple architecture of a visual perceptron. In this case, it's a perceptron of simply the visual system. Like this, you can have a perceptron for like auditory information and so much more. So let's say we have a retina over here. Now, this is going to consist of photoreceptors. These are cones and rods which can detect color, brightness, luminosity of objects that it perceives. Then these are then connected via localized connections to neurons in this projection area A1. And when we say localized connections, it means that specific cones and rods here are going to be connected to very specific neurons over here in this region. Now, the neurons here are then going to be randomly connected to other neurons in this association area A2. And these are also going to be randomly connected to other neuron clusters in these response regions. And we can kind of say that these responses are essentially clusters of neurons that are responsible for some high-level decision-making. And what we mean by that is like R1 could represent like, this object detected a tree, or this cluster of neurons R2 can determine whether we are detecting or perceiving a chair, and so on. So let's take an example here. So let's say that there is like this object over here. It's a tree, but it's an object right now. Now this is going to be perceived by the retina. So light enters the eyes and hits the photoreceptors, such as the rods and the cones. Then specific photoreceptors are now connected to specific neurons here, and these specific neurons will fire, right? And the specific neurons here will actually contain some low-level information. And this low-level information could be like the color of a single branch or a color of a single leaf. This is because they are directly connected to individual receptors that provide very raw, low-level information. Now, these neurons, through the random connections, are now going to be mapped to the A2 neurons. And these A2 neurons are going to have slightly higher level bits of information that are collected here, and these neurons are going to fire. And this could example be like the contour of branches with their leaves. So this is because, a single neuron in this A2 region could be connected to like a neuron in A1 that recognizes a single leaf, and then another neuron that recognizes a single branch, and kind of combining, you can think of combining those pieces of information together to get the information here in A2. And we can also have multiple association areas here and multiple layers to get higher and higher levels of information. And then eventually, this A2 neuron or A2 neurons are going to be randomly mapped to the response cluster of neurons here. And one of these is going to fire. And in this case, let's say it's R1 that fires. Now, once R1 fires, the excitatory feedback from R1 will strengthen the synaptic connections of neurons that caused R1 to fire. So because R1 fired, all of the neurons that fired before this are now going to have very strengthened synaptic connections. Now, this is what happens in a biological case. This is actually what happens in human beings. But what the perceptron is kind of now doing is it is going to do the inverse of this, where instead of excitatory feedback strengthening synaptic connections, we will have inhibitory feedback coming from all of these other responses in order to weaken synaptic connections that didn't fire. Why do we do this? Mostly because of computational purposes. And we will see this actually in like the perceptron algorithm in the future past. So now what happens is, let's say we see another tree again. This is now going to enter the photoreceptors of our retina. And when a tree is seen again, the same assembly of neurons is likely to fire again, firing R1 in the process. So when you see a tree again, it's now easier to recognize because the same neural pathway connection is going to fire and hence elicit the same response. It's a stronger response. And so the photoperceptron has learned to recognize the tree. And this is kind of the high-level intuition of the photoperceptron. And in the next pass, we're going to see a little bit more details about the algorithmic learning process. Quiz time! It's that time of video again. Have you been paying attention? Let's quiz you to find out. Which of the following, according to this diagram, is true? A. A1 will have neurons that capture low-level information, that is raw signals. B. A3 will have neurons that capture high-level information, that is recognition of an object as a whole. C. R1 does not provide any feedback. Or D. If R1 fires, the connections that caused R1 to fire strengthen. Note that multiple options here may be correct, and I'll give you a few seconds to answer this question. The correct options here are A, B, and D. But can you tell me why? Give your reasons down in the comments below and let's have a discussion. Now that's going to do it for quiz 2 and pass 2 of this explanation, but keep paying attention because I will be back to quiz you. In this pass, we're going to look at the algorithmic process for learning in a perceptron. So first we have our artificial neuron here. This is a computation model of a biological neuron. Model, simplified representation. Computation model, the simplified representation of the biological process is going to be broken down in 2 steps that require just calculations and computations. So specifically here, we can consider the inputs as inputs to the dendrites. Now these weights are going to be individual potentials associated with each dendrite due to previous connections. This could trigger now an action potential where we calculate the current membrane potential M, and it fires if it's greater than some threshold potential, or it doesn't fire if it's not. And so you can see how this is the computation model because we broke it down into a set of calculations or computations. Now, this is the architecture of the perceptron, where we have this is the equivalent of the sensory layer. Then we have the association layers, and then we have the response layer of neurons. And instead of localized connections or random connections that we saw in the original paper, we have more full connections to keep simplicity here. Now, let's say that there is some signal that enters the eye. Now, this is then going to propagate in the network where some neurons might fire and some might not. And this is going to be the response where, one of these neurons can determine if it's a tree and the other is if it is a chair. Right? So this becomes a computation model of biological learning and recognition via some visual inputs. So this is kind of our photoperceptron right here. So what is the computation that's actually done in this case? So let's say that we have a data set where the input is going to be 2 values right here, and the output is correspondingly going to be a tree. And we have several examples of this. And it's important to note that while the original perceptron made these inputs as 0s and 1s, we can actually generalize this to be, real value numbers too. So here's the algorithm where we will loop forever. And in this loop, for every input and label pair in the data set, we want to pass it into the perceptron in order to generate a response. And if this response is incorrect, that is, if the response is not the label, we will make updates to the weights in this way. So that is, we will say W is equal to the weight vector plus error times the input vector, right? And this error, it can be either like 1 or -1, depending on whether we got it on one side of the decision boundary or the other side of the boundary. And like this, we will loop through every example in the data set. And only if every single example is correctly identified in the data set, it's only then that we terminate the process. Otherwise, we will keep looping forever. And you can see here that we mentioned before that in the computation model for this perceptron, we're using inhibitory feedback, where we are making updates to the weights in the case of error correction. And we're not just strengthening synaptic connections due to excitatory feedback. And this is for like the computation purpose you see here. Now I'm going to show a demo of perceptron learning right here. And I'll give a link to this little demo down in the description below, because it's not mine. Essentially, we have like a desired outcome, that is the label, which we call as D. We can then calculate the prediction, which is O, determine the error by subtracting the 2, and that's going to be our E vector, or error vector. And if we got it correct, we do nothing. But if E is not 0, that is either +1 or -1, then we are going to update the weight vector. Let's say that now we are going to put a point, let's say right over here. So I put like a red point over here. Let's say the desired feature vector is 1. We then now calculate the outcome. It's going to be 0. We got it wrong, and hence we need to update the weight vector. So the original weight vector was at -6 and +8, but then we will add EX in order to get this new weight vector over here. So if I put like another point over here, you can see that, well, is this wrong? It's going to compute that, the actual is 1, the desired is 1, so there's no error, and because there's no error, we do nothing. And we can do that for any number of points that we put here. There is no change in the weight vector. And so the linear decision boundary also does not change. But the moment I'm going to create a new point over here, which is wrong, it's going to be this green point. Now you can see that that green point is going to be incorrect. Now the weight vector, it's going to be subtracting that input vector, so the arrow goes the other way. It is then, in order to get like -x, and then you add that -x to the weight vector, and that's now going to be the new weight vector. And when you get a new weight vector, you can see that the decision boundary is now going to change in itself. But in doing so, you can see that there still are points even now, this now newly misclassified point over here. But, we can still do some, add new data points here. I added a green data point, which should be correct, so there should be nothing done. But now let's add a point where it will be incorrect. So let's say we add a red data point over here, right? So that's now, we have a new X over there. You can see that we need to now add that vector to the current W. And so the weight vector is updated, and hence the decision boundary is updated. And you can see at this point of time, you can see that we have actually linearly separated all of our inputs, which is great. But in practice, this is just one step, and we can continue to do this again and again, continue iterating over the data set, which is great. So I hope this visual representation and animation kind of helps understand exactly like how these vectors updates are actually happening. And I'll link this down in the description. Now, a pro here is that we have a learning procedure. It's great. And this learning procedure will always find a linear solution that is a linear decision boundary if it exists within a finite number of steps. But the con here is that the learning procedure can be computationally expensive for large data sets. It's a long process. And the data must be linearly separable in order to converge to a solution. Because if it's not linearly separable, you can imagine that the perceptron algorithm will loop forever. Quiz time. Ooh, this is going to be a fun one. How many iterations will the perceptron take to converge to a solution? A, 1 iteration. B, under 10 iterations. C, over 100 iterations. Or D, the perceptron will not converge. I'll give you a few seconds to answer this question. Now, the correct option is D, but can you tell me why? Give your reasoning in the comments below and let's have a discussion. And if you think I do deserve it, please do consider giving this video a like because it will help me out a lot. Now that's going to do it for quiz time and pass 3 of this explanation, but before we go, let's generate a summary. In this video, we introduced the biological process as well as the computation model for the artificial neuron. We also introduced, in the 1940s, the idea of Hebbian learning here, where that neurons that fire together wire together, and introduced this through an example of eye blink conditioning. And using these ideas, we had Frank Rosenblatt create the perceptron, which was a computation model of a biological neural network with the ability to learn from feedback. We also took a look at a high-level diagram of a photoperceptron where looking at an object repeatedly helps these neurons fire more easily, kind of seeing and instigating how the learning process can happen. We then took a high-level look at the architectural diagram of a perceptron and how it is designed in order to mimic, some parts of the visual system, though this can be expanded to other perceptrons. And we also took a look at this inhibitory feedback mechanism of how the perceptron actually learns. So this is its learning algorithm where it'll learn through an error correction update instead of learning through excitatory feedback. And with the demo, we show that this could actually be an effective learning procedure, especially if there exists linearly separable data, but it can lead to issues where the data sets are large because this becomes computationally inefficient, and also if the data is not linearly separable, as it could potentially loop forever. So that's all that I have for you today, and I hope this helps solidify a better understanding of the perceptron and why potentially we would need some more impressive learning strategies, including like backpropagation, which will come at a later place that's more computationally efficient than this strategy. In the last video, we took a look at the perceptron model classifier that was created by Frank Rosenblatt in 1958. And this perceptron model was inspired by the signal processing capability in human sensory systems. Around the same time, Bernard Woodrow and Marcian Ted Hoff were two electrical engineers that were also interested in signal processing, but not in human biology, but in electrical circuits. And in order to understand now why we have these adaptive neurons, we need to understand a little bit about circuits and circuit design. So let's get to that. So this here is a simple circuit, where a circuit defines the path of electron flow. And a simple circuit in the simplest form consists of a power source, a switch, as well as a resistor or a bulb. Now, if we have an open switch, then that means that the bulb is off, which we get the response from. And in a closed switch, we see that electrons can flow, and hence the bulb is on. Now, for this circuit diagram, if we label the switch as X and the bulb as B, we can generate a truth table and also a Boolean expression with the output bulb being represented as some function of the input switch. So closed switch is 1, open switch is 0, and this would be the Boolean expression. Now, this here is a really simple circuit, but circuits can get quite complex. So how do we actually design more complex circuits? Well, in 1939, Claude Shannon wrote a master's thesis in which he actually addressed exactly this and defined the steps for how you can define a circuit. So it involved first constructing a truth table, then creating a Boolean expression from this truth table. Then we simplify this Boolean expression using Boolean algebra, and then you can reconstruct the circuit from this simplified Boolean expression. And what this allowed was that the simple circuit can be constructed using this method. And so circuit design now transformed because of this from an art to more of a science. Now, the con of this, however, is that constructing truth tables can become infeasible if the number of inputs and outputs is very large. For n inputs, there can be 2 to the power of n records in our truth table, which is intractable. So how do we solve this problem? Now, this is where Bernard Woodrow and Ted Hoff come back, and they realize that, well, for some circuits like traffic lights, the accuracy needs to be 100%. Otherwise, it can lead to some catastrophic results, like an accident. However, there are many other circuits which they are interested in signal processing specifically that don't require 100% accurate results all the time, like in telecommunication. Now, so the objective when designing a circuit should not be to minimize the number of components as Shannon had done before, but instead minimize the average number of errors. And so, circuit design by Bernard Woodrow and Marcy and Ted Hoff transformed Boolean algebraic form of designing a circuit to a statistical optimization form of designing circuits. And statistical optimization basically involves techniques like gradient descent. Now, just a note here, at this time, gradient descent did exist, and it was introduced officially, I guess, in 1847 by a French mathematician, Cauchy. Now, to illustrate this statistical optimization, Woodrow and Hoff took a fundamental element that is found in many adaptive circuits. And by adaptive, we mean that the circuit consists of components that can be changed. And in this case, these little knobs over here are voltage gains that can be changed. Now, they also called this circuit a neuron because it is structured similar to the previous artificial neurons, like the McCulloch-Pitts neuron that we discussed in a previous video, as well as later which came on, which was the John von Neumann neuron. And this circuit became known as ADALINE. Quiz time! Have you been paying attention? Let's quiz you to find out. When does circuit design by minimizing the errors make sense over truth tables? A. When you want to simplify circuit connections. B. When the number of possible inputs and outputs is large. C. When errors do not lead to catastrophic results. Or D. When dealing with circuits that cannot be simplified by Boolean algebra. Note that multiple answers may be correct here, and I'll give you a few seconds to answer this question. The correct answers are B and C, but can you tell me why? Give your reasoning in the comments below, and let's have a discussion. Now, if you think I do deserve it at this point, please do consider giving this video a like, because it will help me out a lot. Now that's going to do for quiz time and pass one of this explanation, but keep paying attention because I will be back to quiz you. So ADALINE here stands for an adaptive linear classifier, and why it's called so is going to become more apparent by the end of this pass. So in this pass, we're going to talk a little bit more about some details in explaining the what of ADALINE. So it explains the mathematics and then also uses this in tandem to design an electrical circuit. So let's talk about this. So we know Woodrow and Hoff basically said that they wanted to design circuits to minimize the average number of errors. This is kind of what we saw in the previous pass. And so what they want to minimize is this mean squared error, where this y here is going to be the reference output, the actual output they want in the signal, and this y hat is the output signal of the final electric circuit that they design. Now, this output signal is going to be generated by a signal transforming device called a filter. So essentially, we have an input signal, and the filter circuit is going to take it and generate an output signal. And ADALINE is this filter circuit that we are designing. And we want to adapt the gains, those knobs that we saw before, to minimize the average error. Now, let's kind of map this a little bit to the circuit diagram. So in our ADALINE image, that would be this prediction that we see here. The output of this filter is going to be at this point here, where it's going to be the sum of products of these AIs and XIs. XI is going to be a switch. It's an input switch. And then we want to kind of adjust these knobs, these A's, to minimize the error. So that's kind of what we're saying in the math. And so what we want to do is minimize this equation right over here, where we know this here is going to be the output of the adaptive filter ADALINE. And because we want to minimize, we can take a gradient with respect to AJ. So we take the gradient and then we get this big equation over here. And so how much we need to tune AJ, that is like one of the gains, it is dependent on every single sample. And from an electrical circuit standpoint, this electrical circuit can become really expensive because it needs too many inputs. And so, in order to deal with this, Woodrow and Hoff said, let's approximate the gradient, the total gradient with respect to that single gain, to be the sum of the individual error gradients here. And so, what we can do is go back to the math. And what we want to do is just the mean squared error for a single sample. And right now, we can then take the derivative and we get this equation over here. So we have the gradient with respect to a certain knob for a single sample equal to -2 times the error times the input itself. And so our actual change, according to the, if we apply this to like our gradient descent formulation, is just going to be, we adjust the knob by 2EXJ. And this XJ is going to be just a switch, right? And so if you've kind of noticed here, this is like stochastic gradient descent. And this is thus more practical in electrical circuit design. So armed with this gradient update rule, we now have an electrical circuit that's designed known as knobby ADALINE. So it consists of 16 input switches. It consists of 16 gains, which can be tuned. This is the bias knob over here. And it consists of a reference switch, which is going to give us the true signal that we desire. And this voltage reading during the training phase is going to give us the error, the magnitude of error. And so if we try to transform this knobby ADALINE into a circuit diagram, it kind of looks like this, where we have, again, the input switches here are defined here as +1 and -1. The knobs are the gains here. There's going to be 16 of these. This is the bias gain. And then this over here is going to be an operational amplifier, an op-amp, which can be designed as a summer circuit to essentially take the sum of products of every single one of these. So this could be like A0 plus A1 minus A2 minus A3 plus A4 plus A5 and so on. And I say that because the X's here are just going to be plus or minus 1. And then we're going to get an output continuous value, which is Y hat, which we can compare to the true reference switch value using another operational amplifier. So these op-amps will just take typically the difference between this plus and minus, so that's Y minus Y hat. But if you design the resistors in a certain way, then we can also make it a multiple of this difference. So this eta could just be like any small fractional value. And, this kind of probably looks very similar to like the learning rate in a gradient descent algorithm. Now, given this architecture, let's now iterate through the actual training procedure. So for every single input and label that's in the data set, we set the input via the 16 switches. We then set the reference switch to get whatever label output signal that we want. Then the voltage meter is going to read the error, and it's going to be determined by this formulation over here. Eta is set by how the knobby ADALINE has been designed, specifically the op-amp has been designed. And then we'll adjust each knob according to this formulation that we derive with stochastic gradient descent. And because we derived it with a stochastic gradient descent approach, as we iterate through every single input and label, these knobs will eventually converge to values that will minimize the average number of errors. And this overall algorithm is going to be known as the least mean squared algorithm, or the LMS algorithm. Now, during inference phase, we are now given just an input, and this input is set via the switches. Now, the voltage meter is just going to read the predictions Y. There is no reference that's set. And then we are going to quantize this in the sense of like, okay, whatever y hat is, if it's greater than 0, it's going to read a +1. If it's less than 0, it'll read a -1. And this would be the classification label. And so, in summary, we have ADALINE. It is adaptive because it has weights that can be tuned, the knobs. It is linear because the prediction is a linear combination of the inputs and these adjustable weights. And then it's a classifier. Quiz time. It's that time of video again. Have you been paying attention? Let's quiz you to find out. How do we transform the continuous outputs to get a discrete output from ADALINE? A, directly from the meter. B, using the quantizer. C, using the reference switch. Or D, using the constant source. Note that multiple options here may be correct, and I'll give you a few seconds to answer this question. The correct option is B, but can you tell me why? Comment your reasoning down below and let's have a discussion. Now, that's going to do it for quiz time and pass 2 of this explanation, but keep paying attention because I will be back to quiz you. In this pass, let's compare Perceptron and ADALINE. So both of these are classifiers, and the Perceptron was inspired by signal processing in humans, while ADALINE was inspired by signal processing in electrical circuits. Now, the learning procedure in Perceptron is error correction, so we update the weights only when an error is made. Whereas in ADALINE, the learning procedure is least means squares algorithm. And so on every sample, we will have an adjustment of these gains. Now in the Perceptron, the activation function is essentially just a threshold function, so the outcomes are always discrete. But in ADALINE, the activation function is linear, at least before quantization. Quiz time. Ooh, this is going to be a fun one. Which of the following statements is true? A, the Perceptron was largely influenced by human biology. B, the ADALINE was largely influenced by electrical circuits. C, Perceptron update is a form of stochastic gradient descent. Or D, ADALINE update is a form of stochastic gradient descent. Note that multiple options here may be correct, and I'll give you a few seconds to answer this question. The correct options are all of them, A, B, C, and D. But can you tell me why? Give your reasoning in the comments below and let's have a discussion. And if you think I do deserve it at this point, please do consider giving this video a like because it will help me out a lot. That's going to do it for quiz time and pass 3 of this explanation, but before we go, let's generate a summary. In this video, we talked about ADALINE. ADALINE is a filter circuit that we're designing to adapt gains in order to minimize the average number of errors. We walked through its training procedure, which will effectively follow a stochastic gradient descent approach, all in order to minimize the average number of errors. We also looked at how, from the math, we could construct knobby ADALINE and this circuit diagram, where we define ADALINE to be adaptive because it has weights that can be tuned, linear because the prediction is a linear combination of inputs and adjustable weights with a linear activation function, and then is a classifier. And then we ended with some comparisons between the Perceptron model and the ADALINE model so that we get like an idea of how they exist together. So this here is a biological neuron, and it has many capabilities, one of the most important of which is logic. Now, if we were to connect these neurons as they are in our brain, we notice that certain properties emerge, such as memory. And this capability of memory wasn't there for just a single neuron. And so, John Hopfield in 1981 who was a physicist, posited this question: can such emergent properties arise by connecting individual computation units? And what he meant by this was that, let's say, instead of a biological neuron, we take an artificial neuron. This is specifically the McCulloch-Pitts neuron, which has some inputs, some weights, and an output. And this output is going to be thresholded by a binary threshold value, where it'll fire if it's above some threshold, and it will not fire if the sum of products is below a certain threshold. And if we were to connect multiple biological neurons like this, we can kind of represent that through a computation model that looks like an interconnection of neurons that kind of look like this. And the question that Hopfield is trying to ask is this artificial network now capable of memory? So is it capable of storing and recalling memory? And this here is a Hopfield network. So a Hopfield network is a network of artificial neurons that can demonstrate emergent properties such as storing and recalling memory, error correction, and other capabilities. And in this video, we are going to mostly focus on the emergent property of storing and recalling memory. So let's get a little bit of a high-level understanding of how these two processes work. So how is memory stored? Now, when we consider an interconnection of neurons like this, storing memory is essentially learning itself. And so learning, or memory, is going to be encoded in the synaptic connections between these neurons. And this kind of goes into the Hebbian theory of learning. Now, how is memory recalled? Now, memory is recalled when neurons fire in a specific pattern. So let's now create a computation model to represent these two complex processes of storing memory and recalling memory. And this is often known as associative memory. So now let's construct this computation model. It just means that this is going to be a network which is going to be comprised of a bunch of calculations. So in order to quantify everything, we have each of these, like we mentioned before, are going to be artificial neurons, like the McCulloch-Pitts neuron with a binary threshold unit. And each of them can thus take a state of either 0 when the neuron does not fire, or 1 if there is an action potential and the neuron fires. Now, these edge weights are going to represent synaptic connections, and each of them is going to have a weight that corresponds to the strength of the synapse. Higher a positive value, stronger the connection. Lower the value, then the weaker connection. And this goes in accordance to Hebbian learning, where neurons that fire together will wire together. Now, the overall state of this entire Hopfield network can thus be represented by 6 values. 1, 0, 1, 1, 0, 0, which is basically the states of the individual neurons themselves. So the goal now for us is that this network should represent the two memory processes in the brain, that is, storing information and recalling information. Question 1, how to store a new memory in this network? Well, let's assume that we have this Hopfield network over here, where it has certain synaptic weights, as shown in gray here. And this current state is 1, 1, 1, 0, 0, 1. This corresponds to a memory that we want to store. And so what that means is that we want to somehow encode this information, 1, 1, 1, 0, 0, 1, into the synaptic weights itself. So given the state, we want to update these weights. So how do we do this? Again, this here is going to be a computation model, so everything is going to require calculations. And so Tij is going to be a synaptic connection weight, and it's going to be the sum of all previous states plus this formulation, where VI is going to be one neuron here, and VJ is going to be the corresponding other neuron for this synaptic connection. And so VI and VJ, we know that they can only take two values, 1 and 0. And while this looks like a very intimidating mathematical expression, let's say that we apply the example right here. Essentially, it's just going to add 1 for the cases where the synapses is between neurons that are firing together or not firing at all together. And it's going to add -1 to the synaptic connections where the neurons are firing apart. That is, one of them is firing and another is not, like in this case. And so we just simply add these new weights to the existing weights and update them as such. Now, the next question, how do we recall a memory in this network? So that means given the synaptic connections that we see here in gray, we need to determine the state which corresponds to the memory that we originally stored. Remember, the state is going to be the set of all of these activation values to contribute to an activation pattern in the brain that we saw previously. And so in order to do this, John Hopfield basically made use of the second law of thermodynamics in the sense that the free energy of a closed system should decrease over time. This is a restatement of that second law of thermodynamics. And so what this means is that a stable state would be at this free energy minimum. Now, there's quite a lot of terms here, but just to be very clear of how this physics is going to be related to this computation model that we are creating, when we talk about a closed physical system, in this case, we're going to talk about the Hopfield network, which represents the interconnection of neurons in our brain. And when we talk about free energy, well, we can determine the energy of this Hopfield network using this formulation over here. It looks pretty intimidating, but it's actually very easy in principle. The free energy of this Hopfield network is going to be the sum of synaptic connections between two firing neurons. So let's just take two examples just to illustrate what's going on and how to compute total energy. So in this Hopfield network over here, we have two firing neurons here. Synaptic connection is 0.75. And I think that's the only one that we see here. And so the total energy is going to be -½ times 0.75, which is -0.375. That is the total energy of this Hopfield network. In example 2 over here, in this Hopfield network, well, let's take all of the synaptic weights that correspond to two firing neurons. That's 1 minus 1.5 minus 2. And this is minus 2.5. So applying it to our formulation, the total energy or total free energy of this Hopfield network is going to be -½ times -2.5, which is 1.25. Now, the goal in our Hopfield network is to come to a stable state that corresponds to lower free energy. So in this case, we would like this lower free energy than it is compared to this state. So in order to illustrate this energy versus state visually, we can look at the energy landscape of a Hopfield network. Now, this is going to be a lot easier with an example, which we will show later. So in this energy landscape, it's a plot of the free energy on the y-axis that we just discussed, and the state on the x-axis, which is going to be the set of all neuron states at a given snapshot of time. So what's important to note is that at these energy minimums over here, these are stable states, and these energy minimums are going to correspond to actual memories that were stored. And so the idea here is that we'll start at a random state somewhere up here, and through some updating mechanism of gradually decreasing energy, we should be able to come to an energy minimum here and hence recall a memory. Now, let's actually work through this example here, where we are given synaptic connections and we need to determine the state which corresponds to a memory. Remember, the memory that we stored was 1, 1, 1, 0, 0, 1. And we want to see if we can recall that memory, given that we are using now the same synaptic connections that should have absorbed that information. So this here now is the initial state, where it's not quite right compared to the actual 1, 1, 1, 0, 0, 1. But let's see if we can get to that state eventually. So from this state, we want to minimize the total energy. Now, this current initial state, the energy is 1.25. So in time step 1, what we're going to do now is just choose a random neuron. And let's say that we chose this one. Now for this neuron, we will take the synaptic connection and multiply it by whether the neuron is firing or not, and see if it is above 0. So in this case, 1 times 1 plus 1 times minus 2 plus 1.5 times 0, that's going to be negative 1, and it's less than 0. And so what we do is that the new state of this neuron is going to be 0. And by doing so, we'll see that the energy has decreased from 1.25 to 0.75. So we're actually stepping in the right direction. Now in the next time step, we repeat the process, select a random neuron. Now the total input to this is 0 times 0.75 plus 0 times negative 1, which is 0. So there's going to be no change here, and the energy remains the same. In time step 3, we'll choose a random neuron. Let's say it's this neuron here. And the total input is going to be 1 times negative 1.5 plus 0 times negative 2 plus 0 times 0.75, which is going to be negative 1.5, and it's less than 0, which means the neuron does not fire. So the new state is 0. And then the total energy now, well, there's no two positive, active neurons that are synaptically connected to each other. And so the total energy of this network is 0, which is still good because it's continuously decreasing. Now in time step 4 here, let's say that we chose this neuron. And here, the neuron is going to have an activation of 0. And hence, there's going to be no change in the state. No change in the state means no change in the energy. Now in time step 5, let's say we randomly chose this neuron here again. Now the total input is going to be 1 times 1 plus 0 times negative 2 plus 1.5 times 0, and it's going to be 1, which is greater than 0. So now this neuron turns into a state of 1, and the energy is negative half times 1, which is negative 0.5. Once again, the energy is decreasing. Now in time step 6, let's say that we chose randomly this neuron over here. The total input is going to be 1 times 1.5 plus 1 times 0.75 plus 0 times 0, which is 2.25. It's greater than 0. And so we're going to see that the new state of this is 1 because it's greater than 0. And the new energy, the total energy, is going to be negative 1.625. Now, this is very interesting because what you notice over here now is 1, 1, 1, 0, 0, 1. This corresponds to the state of the original memory that we had stored. And what this also corresponds to is this energy here is minimized. We actually cannot change any of these neurons to get a lower energy. And so we have empirically shown that at this energy minimum, we have recalled a memory. So what this looks like in our energy landscape here is that in the first state, initially, we had 1.25 with this state of neurons here. And as we went forward, we could see that the energy was decreasing over the time steps until eventually we came to 1, 1, 1, 0, 0, 1, which corresponded to our memory. And this was the energy minimum. Now that we looked at this entire Hopfield network, well, there are some pros and cons here. So a pro here is that it's a really simple procedure to determine emergent properties. In this case, we looked at storing and recalling memory or associative memory that we see in humans. It can also be used in error correction or in recovering from corrupt input data, which can also find its uses in content addressable memory. The cons, however, are that we could potentially be stuck at a local minima. So let's say that we have this energy landscape over here for a given Hopfield network, and the actual memory that we want to recall is somewhere over here, in this state right here. And let's say that we start at this state here, but we monotonically continuously decrease the amount of energy we have. So we might only end up in this state, and we can't really traverse this part of the curve because we can only decrease energy, and any updates in state will stop here. So instead, in this case, if we were to have stored this memory and we start here, we might be only able to recall some false memory. So this is wrong. This, however, could be resolved through something called simulated annealing, where we introduce some temperature concept. And so even if we were at this state, we can kind of traverse this little peak here in order to get to this global energy minimum, which corresponds to a real memory. Now, another con here is the limited capacity of Hopfield networks. If there are n neurons that are connected in this Hopfield network, it can really only store 0.14 memories. So for a 6 neuron Hopfield network, it could realistically only store 1 memory correctly without, falling into the trap of recalling false memories. Now, there have been methods to overcome this, such as unlearning or using more complex synaptic connections, and also other learning procedures that come in the future, such as backpropagation. Quiz time. Have you been paying attention? Let's quiz you to find out. A Hopfield network, A, is a computation model of associative memory. B, tends towards decreasing total free energy. C, has a recall procedure based on thermodynamics. Or D, none of the above. Note that multiple options here may be correct, and I'll give you a few seconds to answer this question. The correct options are A, B, and C. But can you tell me why? Please give your reasoning in the comments below, and let's have a discussion. And if you like this video, please do consider giving this video a like, because it will help me out a lot. Now that's going to do it for quiz time and this video, but before we go, let's generate a summary. So in this video, we took a look at a Hopfield network, which is a computation model or a network of artificial neurons that demonstrates emergent properties such as storing and recalling memory, error correction, and more, with an emphasis on associative memory or the ability to store and recall memory. And so we took a look at how this computation model can update its synaptic connections given a memory state. And we also saw how to recover this memory from a randomized initial state. And then we corresponded this to the energy landscape, which corresponds to determining a memory here. And then we elucidated some pros and cons of Hopfield networks. And that's all I have for you today. Now, some more supplemental resources are going to be in the description below, and I highly encourage you check them out for a further understanding of the field. This is a great topic that transcends how artificial intelligence can go towards physics, neuroscience, and mathematics and computation all in one go. And it was a recipient, and well-deserved so, of the Nobel Prize. In the last video, we discussed this interconnection of neurons known as a Hopfield network. Now, this Hopfield network can store data in its edges, and it can also recall data in the form of its state, which is represented as the activations of the neurons. Now, Geoffrey Hinton in 1982 asked how can we use this network to understand and generate data as a generative model. Now, his solution to this was a Boltzmann machine, where the Boltzmann machine structurally is very similar to the Hopfield network with two main differences. The first is that the neurons, instead of being binary threshold units, they are stochastic units that now output a probability. And then the second difference is that we also add hidden units to this network. And that's it. This here is going to be a Boltzmann machine, at least structurally speaking. So Boltzmann machines are stochastic Hopfield networks with hidden units. Now, that's great and all, but what is this? Why do we add hidden units? Why stochastic units? And how does this even learn to generate data in the first place? So we're going to hope to shed some light on all of this in the video. So first of all, why are we using stochastic units? So the idea here is that in a traditional Hopfield network, let's say that this is the energy landscape where we start at some random state. The idea is to minimize energy. But in doing so, in a traditional Hopfield network, as we saw in the previous video, we might get stuck in a local minima when recalling data. And this could lead to false memories that are being recalled. However, in order to circumvent this, a Boltzmann machine will make use of stochastic binary units that output a probability instead. So on certain steps, it becomes possible to increase energy too, and not strictly decrease it. And this allows the network to traverse certain local minima and eventually even settle into a global minima, which is an even lower energy state, and thus increasing the quality of data. Now, why are we using hidden units? Let's say that in this video, we will consider the example of generating a model of 28 cross 28 images. And so, because we want to generate this data, we need the network to understand these images. And so, let's say that we construct this network right over here, which is an interconnection of neurons where each neuron represents a pixel that can either be on or off. And so, there's going to be 784 neurons because it's 28 times 28. Now, each of these edge weights will thus represent the correlation between two pixels in an image. It's a very simple correlation metric that's not that informative. However, let's say now that we add 100 neurons that can learn higher level features. So, for example, a higher level feature could be if we take an image over here, instead of pixel correlations, it can correspond to this bend that we see in this 5. That can be encoded in the edges that are associated with these hidden neurons. So hidden neurons and edges can encode abstract representations of the image that are higher than the pixel level, and hence they become quite useful. So hidden units are quite useful in better understanding the data. Quiz time. Have you been paying attention? Let's quiz you to find out. Which of the following are differences between Hopfield nets and Boltzmann machines? A. The neurons are not binary threshold units in the latter. B. The edges are not symmetrical in the latter. C. The presence of hidden neurons in the latter. Or D. None of the above. Note that multiple options may be correct, and I'll give you a few seconds to answer this question. The correct options are A and C. So did you get it right? Please comment your reasoning down below and let's have a discussion. Now, if you think at this point I do deserve it, please do consider giving this video a like because it will help me out a lot. And that's going to do it for quiz time and pass 1 of this explanation, but keep paying attention because I will be back to quiz you. So right now, we have our Boltzmann machine structurally with hidden and visible units, and we want this network to now be a generative model to generate data. This means that it should understand the probability distribution of states. Now, if we were to translate this more into easy to understand words, and for our specific example, this network should be a generative model of those 28 cross 28 images of digits, And so the network should learn the joint probability distribution of these digit images. And to be crystal clear on like what we want this network to learn, ideally, is that we have the states on the x-axis and the probability of those states occurring on the y-axis. An example of a state could be this 884-dimensional vector, which could be taken up by each of these neurons. That's 784 visible neurons and 100 hidden neurons. And there's going to be thus like 2 to the power of 84 states, like a huge number of them. And ideally, the probability distribution might look something like this, that is going to be learned by the network, where we have high probability associated with the states that we really want. So these will be corresponding to the actual images. And so sampling the network is likely to generate an image of a recognizable digit. So when we sample, we basically mean we take this network, we're going to then perform some sampling. That is, we're going to generate individual states for these neurons. And so we now have a state of the network with 884 values. We will then extract only the 784 visible digits from this, and they will correspond to pixel values. And it will correspond ideally to a realistic number image that is generated, right? But how does the network actually learn to do this, and how does it learn the probability distribution? Well, there's 2 main components that it needs. One is data, and another is a learning procedure. So the data, in this case, is we're going to collect images similar to what we want the model to generate. So it'd be these 28 cross 28 images. And then in the learning algorithm, what we want to do is update those edge weights of the network that we considered. And each edge weight is going to look like an update state that kind of looks like this, where we have 2 terms over here where they might look intimidating, but we'll go through them. One of them is the correlation of the 2 connecting neurons according to the data, and the other is the correlation that is learned by the model. So let's actually take a look at this learning algorithm in practice. So let's say that we have 1,000 such digit images in our training data set. We now have our neural network over here. That's a Boltzmann machine, structurally speaking. And we're going to initialize these edges very randomly, right? And by randomness, it means that a random probability distribution is currently understood by this network. It probably has an equal probability of generating any state. And so if you sample from it, you might get this pixelated image that looks something like this, right? Knows gibberish. So let's just take this neural network. And now we're going to select 2 neurons. Let's just call them neuron I and neuron J. That look like this, as an edge weight of 0.85. And now let's determine that first component in our learning procedure, which is this expectation of, Si, Sj. We said it's the correlation of neurons according to the data. So it's going to be the number of times that both Si and Sj, the neurons, are on, divided by the total number of samples considered. So let's say that after we feed the 1,000 samples in our training set, these 2 neurons will be on 80% of the time. That's 800 times. Then this value becomes 0.8, right? So we'll keep that value aside as equation 1. Now, we need to cycle through the entire data set, thus, in order to compute this value for all edges. And we can do that simultaneously for all edges. Next is the second component, which is this model expectation, which is kind of what is learned by the model, the correlation of these 2 learned by the model. So, and in order to get what is learned by the model, we need to sample values from the model continuously, which we do through something called Gibbs sampling. Now, that procedure works kind of like this. So let's say that you have this network over here right now. What we're going to do is randomly initialize all these neuron states as 0 or 1, right? Now we're going to select one neuron. We select this neuron right over here, right? And we're going to compute the output of this neuron. So what that means is basically taking the sum of products of all of these neurons over here, getting an output, and then we're going to eventually convert this into a probability, right? And then this probability can either be, it can either be a 0 or 1. So let's say in this case, the probability of it being 1 is 0.61 that we get from a computation that will go through and pass 3. Then we can sample from this 0.61 probability distribution, this Bernoulli distribution as we call it, to get either a 0 or a 1, right? So in this case, let's say that the output is 1, right? So now let's just keep it as 1 and we move on to the next neuron. So we then compute this, state for this neuron as well. It could be 0, it could be anything else, and we repeat for 884 neurons across the network in order to get a single state. So the network ends up in, let's say, like this state in the end. And now this is one iteration of Gibbs sampling. And this is because we can take all of these states, take only the visible neurons, and we can construct an image sample, a single image sample from this. So this is one sample. Now, we do this 10,000 times, or basically a very, very large number of times. And in each of these times, we're going to notice whether like these two neurons are firing together or not. In this case, SI is 1, SJ is 0, so they're not firing together. But we're going to count the number of times that they will be firing together, and this is what the model has learned internally. So if we kind of substitute it in our new formulation here, it's going to be the number of iterations in Gibbs sampling, where SI and SJ are 1, divided by the total number of iterations in Gibbs sampling. Let's say that, of the 10,000 iterations that we did, the two neurons I and J fired 4,200 times correctly together, right? That means that the correlation is 0.42 of the model. So now that we have our components in this learning algorithm, we can kind of just substitute and compute. So we can substitute these values, 0.48 for the correlation of these neurons with respect to the data, then 0.42 with respect to the model. Take the learning rate to be, let's say, 0.1, just to see how the magnitude of the jump that we want to make for the weights. And the initial edge weight was 0.85, and after the computation, it now becomes 0.88. So it strengthens the connection in this case. So essentially, basically, we took this network, we took neurons I and J, 0.85. That's going to now be updated to 0.88. And we would update all of the edges simultaneously, since the updates can be computed for all of these edges simultaneously too. And that's going to be one iteration of this entire procedure. So now we repeat this entire procedure entirely many times until the weights do not change anymore, or specifically the correlation that the model has learned doesn't really change as much. Now, this network now is a Boltzmann machine that has learned the probability distribution of digits. So I just replace its weights with like new weights right now that it could have potentially learned. Let's say that this is the network in the end state. So what that means is we can now take this network, we can perform sampling, that is like Gibbs sampling, taking one neuron, kind of randomizing everything, taking one neuron at a time in order to compute the actual sample for all the 884 neurons here. We can then extract only the visible 784 neurons, arrange them like a 28 cross 28 grid in order to get a generated image. And this is going to be a realistic image of a digit. And so this model is now a generative model. Quiz time. It's that time of video again. Have you been paying attention? Let's quiz you to find out. When correlation of neurons according to the data is smaller than the correlation according to the model, the synaptic connection strength between the neurons, A, increases, B, decreases, or C, remains the same. I'll give you a few seconds to answer this question. The correct option is B, but can you tell me why? Please give your reasoning down in the comments below, and I would love to hear them. Now that's going to do it for Pass 2. Now it's going to do it for Pass 2 and Quiz 2, but keep paying attention because I will be back to quiz you. In this pass, we're going to go through some physics and math expositions here just to tie everything up together and answer some unanswered questions. The first of which is, why is this even called a Boltzmann machine? because here we have this neural network architecture that we constructed. Now, this is an energy-based model based on the Hopfield networks, right? So Hopfield networks are energy-based models that minimize energy. And so is this Boltzmann machine, technically speaking. But we know that we saw throughout this video that we constructed a generative model that maximizes probability. So how are we able to reconcile minimizing energy and maximizing probability of a state? They should essentially be the same, but where is that link? And that link is exactly what is given by the Boltzmann distribution. So the Boltzmann distribution is going to be an exponential distribution where they are related as such, where we can see here that if we decrease energy, we're going to increase effectively probability. And so hence the link. Now, the second question here is, in this Boltzmann machine, we have these neurons and we just called them binary stochastic neurons, but what exactly are they doing? So you know that in a normal Hopfield network, all of the neurons are binary threshold neurons. That is, we have inputs over here with some weights. We'll take a sum of product and we'll determine an output based on some threshold. If it's greater than that threshold, it's 1. Less than that threshold, it's 0. But in this Boltzmann machine, we use binary stochastic neuron. So when we take an input, we get the sum of products, but we'll pass it through a logistic activation function in order to get a probability value. And then we will sample from this probability distribution that's created, which is like a Bernoulli distribution, where the probability of firing is 0.81. And when we sample from it, we can either get a 0 or a 1. Now, why on earth here, though, are we using a logistic activation function? Well, we can actually derive this equation. Now, I'm just going to show you the derivation on screen, but I can link it down in the description below, and you can kind of check these steps out. But effectively, we're going to get the probability that a neuron is going to be 1 is going to be 1 divided by 1 plus the exponent of this energy-based term, where delta EI is known as the energy gap, KB is the Boltzmann constant, and T is a temperature to indicate noise, which we will indicate next. So energy gap here is energy of the network when the state is 0, and minus energy of the network when the neuron state is on. And this logistic function is the probability that the neuron state is 1. So let's actually walk through what this entails for different cases. So let's say that case 1, we have a temperature of 0. This temperature 0 implies that, well, the probability that neuron will fire is 100% if delta E is greater than 0. That is, if the state 1 brings the network into a lower energy state, then the neuron will fire, so we can get into that lower energy state. Similarly, the probability that the neuron will become 1 is absolutely 0% if transitioning to that 1 is going to make it into a higher energy state, which is not what we want. And so if temperature is 0, our network is definitely going to take the steps to monotonically decrease energy on every step. This is going to be exactly what a Hopfield network does. Now, let's see what happens in case 2, where we take another extreme of temperature being infinitely large. In this case, if you kind of substitute it over here, you'll see that the probability that a neuron fires is going to be 50-50. And it essentially means it's a very noisy update, which is independent of energy transitions. And so this kind of brings us to a case 3, where the probability of a neuron firing is going to be greater than 0.5 if, transitioning to a state 1 is a lower energy state. And this is what we do in a Boltzmann machine in order to escape local minima. So this temperature acts as noise. Now, question 3. How do we derive this learning rule over here? So this learning update is actually quite simple and very clean to look at. And its derivation can be a little bit involved, but it involves maximum likelihood estimation. Now, there's a really good slide deck that derives exactly this from the University of Toronto, where they do the likelihood estimation calculation in a few slides. So they do like the first term derivation, and then they do the derivation of the second term, and then they can combine them right here into the update rule that we see. So I'm going to link this down in the description below so you can check it out and go through it. Now, last question. how long do we need to train a Boltzmann machine? So let's take a look at this probability distribution graph that is currently learned by the model on every iteration. So in the beginning, the model is going to have assigned random weights. So basically, the probability distribution that is understood by the model is going to be random. And so it would generate, pixelated gibberish. But as the states go on, what we will see is that the probability distribution is going to eventually converge to a point where this distribution no longer changes. And this is when this distribution has hit thermal equilibrium. And if we sample from this distribution in the network with Gibbs sampling, we should see realistic digit images if it has been trained correctly. Quiz time. Ooh, this is gonna be a fun one. If all the inputs to a neuron in a Boltzmann machine are 1, then the output of the neuron is A, 1, B, 0, or C. It can either be 0 or 1. I'll give you a few seconds to answer this question. The correct option is C, but can you tell me why? Give your reasoning in the comments below and let's have a discussion. And if you think I do deserve it at this point, please do consider giving this video a like because it will help me out a lot. And that's going to do it for quiz time and pass 3 of this explanation, but before we go, let's generate a summary. To summarize, we took a look at a Boltzmann machine, which is a stochastic Hopfield network with hidden units, and we trained this to be a generative model. We then explain how this Boltzmann machine can learn the probability distribution to generate realistic digits by collecting data, as well as using this learning algorithm, where we try to look at the correlation that is between two neurons according to data, and the correlation that is learned between two neurons by the model. And we would perform this update until it reaches convergence. And once training is done, we can then sample the states in order to then extract visible units to get a very realistic image of a digit. And over the iterations, we see that what's happening is that the probability distribution changes until it converges to a point of thermal equilibrium where the states corresponding to the highest probability are the ones that correspond to the most realistic digits, which is what we saw in the network. So in 1958, Frank Rosenblatt invented the perceptron, and the perceptron was a computation model of the biological process of pattern recognition. A model is a simplified representation of a complex process, in this case, pattern recognition. Computation model means that we can boil this down into a set of sequence of steps, calculations, or computations. Now, this here is going to be the computation model for the perceptron, the original perceptron, with its single learnable layer over here. Now, these are going to be binary threshold units, where there's a single weight layer. We have input features, and we have an output response. And the weights here are going to be learned by the perceptron convergence learning procedure, which we have done a lot more in a previous video. Now, while the perceptron can have multiple layers, so this is a multi-layer perceptron that was created by Frank Rosenblatt, it is really only this last layer over here that has learnable parameters. Now, how do we get the multi-layer perceptron? So an important note I want to make in this video is that in 1958, Frank Rosenblatt introduced indeed a multi-layer perceptron, but only the last layer was learnable. However, that is not specifically the architecture that we refer to as the multi-layer perceptron today. And there are 3 main differences. And when I say multi-layer perceptron, I'm referring to this new architecture. And For the sake of separating the two, I'm going to refer to the previous multi-layer perceptron that was introduced by Frank Rosenblatt simply as the perceptron model, or just the perceptron architecture, just to distinguish the two. With that cautionary PSA out of the way, let's continue. So this here is the perceptron architecture, the original perceptron architecture. Now, in order to convert this to a multi-layer perceptron, as we call today, we will introduce hidden units. These hidden computation units are going to be non-linear functions. So we introduce hidden layers with non-linear neuron units. And then we replace the perceptron convergence learning procedure with the backpropagation of errors learning procedure. And this is now what we call the new multi-layer perceptron as we understand and call it today. So to convert the original perceptron to the multi-layer perceptron, we have made these three changes. We've added hidden units. These hidden units are nonlinear computation units. And we've also replaced the perceptron convergence learning procedure with the backpropagation of errors learning procedure. But why are we doing any of this at all? And in this video, we're going to take a look at each of these 3 points to understand exactly why and how they work. So first of all, let's talk about hidden units. So our perceptron architecture can actually work really well if we have very good handcrafted features. So for example, let's say that we are trying to build a pattern recognizer to recognize a 2-digit from a non-2-digit, where the input could be like some input 28 cross 28 image of a 2. Now, what we can do is if we just have 4 features, we can handcraft these 4 features. Let's say one of them could be fraction of pixels that are on the top half of the image, the fraction of pixels that are on the bottom half of the image, that on the left half, and then on the right half. These could be plausible features to recognize a 2 from not a 2. And assuming that these are good features, then the perceptron can actually work pretty well. But the problem here is that crafting good features is very much a trial and error mechanism, and it can be extremely tedious and difficult to get the right features. So, how do we deal with this? Well, instead of handcrafting features with hidden layers added, we can now just pass in the raw input directly. So we don't need to handcraft our 4 features from this image. What we can do is just pass the image directly, where we have this input layer of neurons, which is 784 neurons, 1 neuron that can represent a pixel. And then each of these hidden units could thus represent meaningful features to recognize a pattern. So for example, this neuron could recognize just the top hat of this 2. This neuron could recognize some other edges over here. This neuron could recognize the shading and luminosity of these edges. And so each of these could just detect their own features. And hence, hidden units are known also as feature detectors. So, why do we have hidden units? I hope this makes more sense. Next, these hidden units also need to be non-linear hidden units. So, why is this the case? I'm going to represent non-linearity with this tilde symbol inside the unit to represent that it is not just like a binary threshold neuron. So in the event that it is just a linear neuron, all of these hidden units are linear neurons. When we pass in an input, the output is simply going to be a linear combination of the input if you just work out the math. And if the output is a linear combination of the input, what this means concretely is that if this is the input state space, in this case, it could just be, if there's like 4 neurons, this could just be 4 axes or 4 dimensions, in a space of which we have either 2s and non-2s. If we only have linear hidden units, then the decision boundary will also be linear in its inputs. So the equation of this decision boundary would just be ax1 plus bx2 plus cx3 plus dx4. Hence, it's going to be a hyperplane that's linear. And because it's a linear hyperplane, it may not classify the patterns correctly. And most pattern recognition problems that we would like to solve typically are a little bit more complex and have some non-linearity like this to it. And so, in order to solve this issue, we can introduce non-linear hidden units. With non-linear hidden units, if you pass in certain inputs, you will get a non-linear function of the inputs at this output neuron. And what that means is that the decision boundary is now also going to be non-linear in the inputs, and it can thus better categorize and recognize patterns. So now let's move on to the third change that we made, which is we introduced a new learning algorithm. So we have these neurons here that are hidden neurons. These need to learn how to detect good features. But in order to learn how to detect good features, it means that these edge weights that are hidden over here need to also be learned to generate good features. Now, the perceptron convergence learning procedure, though, can't really be used here, because in the organization of the perceptron that was introduced, we see that while the perceptron, the original perceptron, could have multiple layers, it's only this last weight layer that is actually learnable here. But the big question here is now, why can't we use perceptron convergence? Well, let's actually take a look at this with an example. This is a very simple example with one neuron per layer. It's a multi-layer architecture, and we want this neuron to learn how to function as an AND gate. So whenever the inputs x1 and x2 are on, y should be on. Otherwise, y is off. Now, let's say the weights are W, the outputs of each neuron is represented by O. And the weights are initialized to 0.5, and assuming these are just binary threshold units, they are just going to be 2. So we'll take that aside, and now let's try to use the perceptron convergence learning theorem to actually learn these weights. So let's say the input is x1 is 1 and x2 is 1. So if we pass 1 and 1 over here, the output you're going to get is 0 for assuming these are binary threshold units. And this is incorrect because the output should have been 1 for this. And according to the perceptron convergence learning procedure, every time that there's an error that's made during training, we're going to have to update the weights. So let's update W31 over here. And this is how the weight update is going to look. So it's the learning rate eta times the error that was made times the input. So the weight is now going to be, if you kind of look at this and do the math, you'll see that it's going to be 0.5. And here we needed to calculate what O2 would be. This was the input to this neuron, but we can calculate that just by running a forward procedure over here. So weight W31 doesn't change, but at least we were able to compute the new weight. That's great. Now let's try to do the same for the weight W21. So let's go into W21, which is right over here. It's going to be, again, the learning rate times, well, it's going to be this output that we get, which is O2. That's the desired output is going to be O2 minus the projected output that we get with the forward pass, which is O2 hat, times the input, which is O1. That's the input to this neuron. Now, you realize here, though, that we actually don't know what O2 is. Like, what is the desired value of O2? We really don't know any of that. And so, the perceptron convergence learning procedure cannot be used to train the hidden weights, but it can be used to probably train just the last layer. And so, we need a new learning procedure that can learn all the weights in the network and not just the final layer. And we can do this with a new learning algorithm known as the backpropagation of errors. And I've discussed the backpropagation of errors learning procedure more in another video, so do check that out for some more details. Quiz time. Have you been paying attention? Let's quiz you to find out. Which of these 4 networks has the ability to learn a non-linear decision boundary? Note that multiple answers may be correct, and I will give you a few seconds to answer this question. The correct options are A and B. Did you get them right? Give your reasoning in the comments below and let's have a discussion. And if you do think I deserve it, please do consider giving this video a like because it will help me out a lot. Now that's going to do it for quiz time and this video, but before we go, let's generate a summary. So we started this video with a definition of a perceptron. It's a computation model of the biological process of pattern recognition. Now, Frank Rosenblatt also introduced a multi-layer architecture to this perceptron, and so we call it the multilayer perceptron. But only the last layer is going to be learned here. However, there have been additions of nonlinear hidden units so as to learn more complex decision boundaries, as well as a new learning algorithm so that we can learn all weights and not just the weights that are associated with the final layer. In our last video, we looked at multi-layer perceptrons and mostly asked the question of why do we even need backpropagation? And the answer to this is that in our multi-layer perceptron, which has multiple layers, we add multiple layers of nonlinear units so that we could recognize more complex patterns. Now, these non-linear hidden units are supposed to be good feature detectors, and they have to learn to be good feature detectors. And what this means is that these edge weights over here that connect or input to these hidden units should also be learned as well. And the perceptron convergence learning procedure, which we had typically used in the perceptron architecture, cannot be used to learn the weights of all layers. And to understand exactly why this is the case and why it can only learn the weights of this last layer and not these other layers, I encourage you to check out that previous video. Now, because it can't learn the weights of all layers, it necessitates the need for a new learning procedure. And the new learning procedure that we even use until today is the backpropagation of errors. So, some questions that we are going to look at in this video is, for one, how did backpropagation evolve to be what it is today? And two, towards the end of the video, we're going to look at a little bit of an exposition about who invented backpropagation, a deceptively simple question with an extremely complex answer. So let's get to it. So in order to describe the evolution of backpropagation, let's now consider a very simple equation. We have y is equal to a0x plus a1. X is the input, y is the output, a0 and a1 are parameters. And let's say that we make a bunch of observations of x's and then we record the output y. Now the goal would be to find these parameters a0 and a1. So how would we do this? Well, in this case, there are observations which we can plug into this equation. So there's more equations than there are unknowns, and we can easily solve for a1 and a0. So the method that we use, whether it's method of substitution, elimination, these are analytical methods. Now, unfortunately though, analytical methods are not very practical for more complex cases. Now, let's go to the first person in our story, who's Cauchy. Back in 1847, he's a French mathematician who wanted to understand the orbit of planets. Now, analytical methods, though, could not really be good at solving these problems. So when we're talking about more complex problems, compared to our little simple one here, more complex problems would have more unknown parameters. They also have more observations that are being made. There's also a potential nonlinear relationship that exists between the inputs and the output. And to top it all off, there might be noise in the system, so there's no real exact solution. So in this case, an analytical method may not be feasible to solve this problem, to find the parameters that exist here. Now, in order to solve this equation, that is, understand what the values of those individual parameters could be, we could use a numerical method instead. And the general guideline of a numerical method involves 4 steps. So start with the guess, you determine the cost of the guess, you make very small nudges or changes to the parameters to reduce that cost gradually, and you repeat step 2 and step 3 until you finally reach a cost that is acceptable. Now, the goal overall of a numerical method would thus be to enable parameters to converge to an approximate solution guided by the cost. And one such numerical method that Cauchy introduced back in the 1840s would be known as gradient descent. And it kind of looks like this, where, the step 1 that we mentioned was starting with a guess. So let's say that the problem that Cauchy wanted to solve can be bubbled up to look like this. Specifically, we could say that, y could be the position of the planet along the orbit, since that's what he was interested in. Some parameters could be like velocity, others mass. This essentially would just be like a big differential equation. And then we have some noise in the system as well. And now we can start with a guess for the parameters a0 through an for n parameters. Step 2 is now to compute a cost of this guess. Let's just say that the cost would be the error, so the squared error of what we observe as the orbital position to what is predicted by our model for orbital position across all samples. And then what we're going to do is use this very magically looking equation to decrease the cost, where we nudge each parameter by eta times the gradient of the cost with respect to that parameter. Now here, the negative gradient represents the direction in which you want to change the parameter, and then eta represents the magnitude of what you want to change the parameter. This works because the direction of the gradient vector is the direction of steepest ascent. So just to pause and ponder, I'm going to repeat that again. This works because the direction of the gradient vector is the direction of steepest ascent. So let's get into the details of what do we mean by this. So what is this gradient vector, first of all? So this gradient vector can be represented by nabla j, and mathematically it is a vector of the partial derivatives of this j with respect to each parameter. And what we are saying now is that this vector is essentially going to correspond to the direction of steepest ascent. So if I were to say this in much simpler English, is that let's say that we have like an n-dimensional space or an n+1 dimensional space where we initialize parameters a0 to an, and that's a single point. Now, what direction do we need to move in order to maximize the change in this j? And well, the answer to that is what we're saying is that if we, nudge the parameter a0 in the direction of delta j by delta a0, nudge the parameter a1 in the direction of delta j by delta a1, so on, all the way, we would nudge an slightly in the direction of delta j by delta an, then this would correspond to the maximum jump that we could possibly make by nudging these parameters. Now, it sounds like a mouthful, but honestly, it'll probably be more clear if we show this visually with some simple examples. So let's consider this first example where we have like a very simple function j, which is x squared plus y squared. Now, if we take the gradient of this and we compute the gradient vector, it's going to be 2x and 2y. Now, what we are trying to imply here is that, let's say that we started a point x, y. If we wanted to determine the direction of maximum ascent of j, then what we would need to do is nudge this point in the x direction by 2x and nudge the point in the y direction by 2y. Now, let's see what that looks like more visually in a graph. So I've come to this 3D plotter here just so that we can visualize what's going on. Now, let's say that our function is for this x squared plus y squared. So this is going to be like a nice parabolic shape where the z-axis is going to represent the cost, and then we have the xy plane, which represents our parameters. Now, what we're going to do here is we're going to add a vector field. And this vector field is essentially going to be for every single point xy, it's going to determine what is the direction of the gradient vector. So in this case, our gradient vector, what we want to point to is going to be 2x and 2y. This is exactly what we computed by hand previously. And so if I enable this vector field to be visible, you can see that, for every single point on this curve, like if we were at this point, which is like right here on the curve, what would be the direction of the gradient vector? It would be in this outward direction. So it'll be like, it would go upwards. Similarly, if, at this point, the direction of the gradient vector is also pointing outwards here. And so on, we can see that for every single point. Now, what we claimed now is that the direction of this gradient vector actually is the direction of steepest ascent, which, if you kind of just look at this, it is true, right? Like at any point that you can see, whether it's here on the cost function, you could see that the direction of the gradient right here, it actually does correspond to the direction that you would want to go to ascend this curve. Even from here, you can actually try this out with any point. And so this vector field actually gives us a good schematic representation of, at every point, what is the direction of the derivative. And we can visually see that the direction of the derivative at any point is truly the direction of steepest ascent. Now, just to hammer home this point, let's look at another example where j is equal to xy now, and we compute the gradient vector to be yx. So to be clear, what we mean by this in English is that, if we start at some point xy, in order to get the maximum gain in j, we would need to nudge this point in the x direction by y and nudge it in the y direction by x. And if we go back to our plotter, let's actually enter this in our plotter here. So let's see now the new value of z, let's say that it's xy. Okay, let's get rid of our vector field right now. So you can see, just to visualize it, it's a little bit tilted, but now you can see in the x, y, and z direction how this kind of looks. So just before I create the vector field here, which is going to be for y and x, which is what we computed by hand just now of the gradient vector, before I enable this vector field, I want you to take a moment to see what you think the vector field is going to look like. All right, have you thought about it? Great. So let's enable this vector field and see what's happened. All right, so remember, the vector field is going to give the direction of the gradient at every single point along the xy plane. But you can also see that, if you look at this, this is the cost function right here, that, at every single point here, in order to go up, we can see that it's actually in the same direction as that of the gradient vector. And so we can visually see that the gradient vector once again gives the direction of steepest ascent. Now, this isn't really a proof, but it is a nice visual guide to just show that this is true. And I can link to formal proofs more mathematically down in the description below. And so what we can see here is that this delta j, delta ai, is going to be the direction of steepest ascent. And hence we take the negative of this direction because we want to go down and descend because we want to minimize this cost. So I hope that adds some more intuition on what this gradient descent update rule is actually doing and why it exists the way it does. Okay, so this gradient descent method relies on us to compute the gradient with respect to every parameter. But this computation of the gradient can become very expensive. We have to compute the partial derivative, after all, with respect to every single parameter. So how do we deal with this? Well, we can use efficient methods to compute the gradient vector. So one such efficient method is known as reverse mode automatic differentiation, and another is the adjoint state or co-state method. So we're going to talk a little bit about automatic differentiation, and this second one has been used parallelly in the 1950s with respect to control theory, but a little bit more on that later. So let's say now we want to solve the problem of z is equal to xy plus sine x, and we want to find the gradient vector of z. So in automatic differentiation, what we would do is we would take this problem and kind of rephrase it. So let this first term be a, the second term is b, so z here, or z, is equal to a plus b, and we want the gradient of z with respect to x and gradient of z with respect to y. So from this, let's try to create this computation graph. So what this means here is that if there's an arrow from x to a, it means that a is a direct function of x. So you can see that x and y are just their own independent variables. A is now dependent on x and y, b is dependent on x, and z is dependent on a and b, which is representative of these equations. So let's just take the forward pass of automatic differentiation just to show its inefficiencies. So first, to do this, let's add a variable t here, an independent variable. It can take the value of x or y, which we will see later. So right now, x is simply going to be a direct function of t, and so is y. So what we can compute at this point is that first we can compute the partial derivative of x, or the derivative of x with respect to t, as well as the derivative of y with respect to t. No problem. Next, what we can do is we can compute the partial derivative of a with respect to t, as well as b with respect to t. Putting all of it together, we can compute the derivative of z with respect to t. Now what we can do is, like, say if t is just x, we now have a method to compute the derivative of z with respect to x. Now we can do another forward pass where t is equal to y, and then we can compute the derivative of z with respect to y. So this provides us a method to compute the gradients of z with respect to every variable. But this forward mode requires O of n forward passes to compute the gradient vector for n parameters. And this can be quite inefficient, especially for a larger number of parameters. So let's now talk about the reverse mode automatic differentiation and see how that can be more efficient. So in this case, we start from the end, where is the derivative of z with respect to z, which is just a seed of 1. From this, we can directly compute derivative of z with respect to a and derivative of z with respect to b. Z is, after all, a plus b, so you can directly compute these two derivatives. So that's great. From this, using chain rule, we can then compute the derivative of z with respect to x and derivative of z with respect to y, as it's a function of these partial derivatives using chain rule. And so what we can see here now is that in this reverse mode, we only needed one backward pass to compute the gradient vector for n parameters. So you can see how efficient this method can be. Now, for more technical details on this and even code, I'm going to link this blog post right here in the description below, so I encourage you to check it out. Now, I guess you can see now how you can use this method in neural networks. So let's say that we have our neural network over here, where we have the prediction that's coming as the output of the neural network. Then we will now compare it to the observed value in order to generate our cost j. And you can see now from the reverse end, we can start with the partial derivative of j with respect to j. It's just 1. But we can then compute the partial derivative of j with respect to y pred. It's an easy computation. And then what we can do is continuously use the chain rule in the reverse direction, like we saw before in our computation graph, in order to get the partial derivative of the cost with respect to every single edge weight or every single parameter in the network. And all of this basically just required one backward pass to compute all the gradients. And hence, this becomes an efficient method to learn the gradient vector in a multi-layered network. And hence, it could also be used in the gradient update equation pretty easily. So this here is kind of the evolution of how backpropagation came to be and how it is now more efficient. Now, the next question I wanted to answer in this video, or at least attempt to try to answer, is who invented backpropagation? Like I mentioned in the beginning of this video, it is a very deceptively simple question with a complicated answer, because backpropagation was invented multiple times by multiple people from the 1950s through the 1980s. So let's just list out a few people and where and how they kind of fit into this entire story. So we'll start in 1960 with an aeronautics engineer, Henry J. Kelly. And in 1960, he wanted to understand the optimal flight path from Earth to Mars. And in order to do so, he invented a modification of the adjoint state method, which was itself another kind of modification of the backpropagation method, as the flight path and also the constraints were differential equations. And so he needed an efficient way to solve these equations. In the 1960s also, Bryson and Ho laid out a framework to solve problems in control theory. And they also invented a version of backpropagation that could be used in controllers. Control theory is a branch of engineering that can be geared towards understanding how to create automated systems. Then we have Seppo Linenmaa. In 1970, he wrote a master's thesis that describes reverse mode automatic differentiation. Now, this was an unpublished work, however, at that time. And in 1974, we have a publication by Paul Werbis, where he published the first version of backpropagation to a multi-layered perceptron. He apparently came up with the idea almost a decade prior, but there were problems along the way for him to try to get to publishing this. In the 1980s, we saw Jan LeCun, who also described a version of backpropagation in his PhD thesis to train neural networks. But probably the most famous among all of these is the 1986 publication by Rumelhart, Hinton, and Williams. So through the 1980s, they had created a version of backpropagation that we even use today. And after this point, there wasn't really much a rediscovery or reinvention of backpropagation. They are also responsible for popularizing backpropagation in general as a learning procedure. Now, I found a really cool blog post of all of this backstory relating to backpropagation, and I'll link it down in the description below because I thought it's a super interesting read. Quiz time. Have you been paying attention? Let's quiz you to find out. What is the main advantage of backpropagation over the perceptron convergence learning procedure in neural networks? A. It could solve partial differential equations efficiently. B. Parameters in all hidden layers could now be learned, and not just the last layer. C. It enabled a multi-layer network to model complex nonlinear relationships. Or D. It provided a systematic way to minimize the overall error using gradient descent. I'll give you some time to answer this question. The correct answer is B. Did you get it right? Leave your reasoning down in the comments below and let's have a discussion. And if you think I do deserve it at this point, please do consider giving this video a like because it will help me out a lot. Now that's going to do it for quiz time, but before we go, let's generate a summary. The perceptron convergence learning procedure, which was used by perceptrons to learn, could not be used for a multi-layered architecture, and so we use backpropagation of errors. But how did backpropagation evolve to be this algorithm, and who invented it? We saw that for very complex problems, analytical solutions may be infeasible. And so, in order to solve these, we could use numerical methods instead. One such numerical method was developed by Cauchy, known as gradient descent. In gradient descent, we start with a guess for the parameters a0 to an. We then compute the cost, and we then update the parameters by nudging them in the direction of steepest descent. This delta JA by delta AI is the direction of steepest ascent. The negative sign means the opposite direction of that. And eta is going to be the magnitude of the jump. But the computation of the gradient vector can be quite expensive. And so we also discussed efficient methods to compute the gradient via reverse mode automatic differentiation or the adjoint state method. While the forward mode requires O of n forward passes to compute the gradient vector for n parameters, the reverse mode only requires one pass to compute the gradient vector for all parameters, making it far more efficient. And so this efficient computation is also used in neural networks today. We also saw that backpropagation was invented multiple times by multiple people from the 1950s through the 80s. We had a few of these cases that came from optimal control theory. We also had some coming from master's theses and also PhD theses. And then we have the most famous version of backpropagation, which was Rumelhart, Hinton, and Williams in the 1980s. That became more popularized even today. And that's all that we have for today. I hope that this video helped shine some light onto why we have this backpropagation learning procedure today, and also some of the visualizations that surround intuition of this too. And so that is the evolution of neural networks, at least the early versions until backpropagation. Thank you all so much for watching, and I'm going to link down some resources in the description below to continue your journey into this amazing field. Click on the video over here to continue your AI journey, and I will see you in the next one. Bye-bye.